This video will talk about satellites. First of all, a satellite is just a small object that is orbiting around a massive object. And back in the day, it was Newton that realized it was only the force of gravity that caused these satellites to orbit. Now imagine if you were to fire a cannonball horizontally from a very, very tall mountain. As the cannonball falls, the Earth will also curve away. Therefore, this cannonball would be continually circling the Earth at the same altitude. This is the definition of a satellite. So, an orbiting object, or any satellite, is both falling towards the Earth and moving at a tangent to the force of gravity. Therefore, we can draw a free body diagram. So if this was Earth, and you have a moving satellite, it is moving at a tangent to the direction of the force of gravity. So now let's look at some equations. From our free body diagram on the last video, we know that the only force applying on the satellite is the force of gravity. So Fnet equals Fg. We can then replace Fnet with ma, but not just ma, but mac, because this satellite is undergoing circular motion. On the other side of the equation, we have Fg. In the past, we've been substituting Fg equals mg. However, this is no longer the case because this object, these satellites, are not near the surface of the Earth. But we can replace Fg with our universal gravitation equation, Fg equals big G times m1, m2 divided by r squared. In this case, m1 is our satellite, the object undergoing circular motion, and m2 is the source of our gravity, in this case, Earth. So now we have mac equals g, m object, mass of the source, divided by r squared. Notice that we can replace ac with v squared over r. So now we have this equation. And notice also we have mass of the object on both sides of the equation. Therefore, we can simplify and cancel it out. Solving for v squared, we have v squared equals g times the mass of the source divided by the radius. Also notice that we've simplified one of the r's, and one of the r's cancel out. So we have this equation, v squared equals g times mass of the source divided by r. This equation, when square rooted, will give us the velocity of our satellite. However, if we're to find period of the satellite or the radius of the satellite, we can replace the centripetal acceleration equation with now 4 pi squared r divided by t squared. Once again, we can simplify the equations by canceling mass of the object. And also notice that we can collect like terms in forms of the r, which is both here and here. We cannot cancel them out because they're not on both the numerator side or the denominator side. However, we can collect like terms and get r cubed equals t squared times g times mass of the source, all divided by 4 pi squared. These two equations are key to studying satellites. However, you should not need to memorize them because you can always derive these equations from our net force equation, Fnet equals the force of gravity. You can then substitute Fnet with m times centripetal acceleration, and g, you can always replace it with the universal gravitational formula. From then on, you need to look at your problem. If you need to find velocity, you need to replace ac with v squared over r. However, if you're looking for a period, or you have a period in your problem, then you can replace your ac with 4 pi squared r divided by t squared. And then you can go on and simplify your equations to find the variables that you're looking for. Let's try our first example. In this example, we're asked to find what is the velocity of the moon, so v equals question mark, if the center of the moon is 3.84 times 10 to the 8 meters, so that is our radius of circular motion, from the center of Earth, and we're also told that the mass of the Earth is 5.97 times 10 to the 24 kilograms. So once again, we can start with a free body diagram. Here's the Earth, here's the moon, and the only thing affecting the moon is the force of gravity. So then Fnet equals Fg. We can replace Fnet with MAC, and we can replace Fg with big G and mass of the moon, mass of the Earth, all divided by r squared. And on this side, this should be mass of the moon. Okay. So now we notice that the mass of the moon can cancel out. So that's gone. We can now replace centripetal acceleration with one of our centripetal acceleration formulas. And because we know we are looking for a velocity, we can replace AC with v squared over r. And on the right-hand side, it's still big G, mass of the Earth, divided by r squared. And we're looking for v, so let's isolate for v. So then v becomes big G, mass of the Earth, all divided by a single r, square root of everything. Also notice that one of our r cancels out on this previous equation. Now we can substitute v equals 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared times 5.97 to the 24. I don't have room for units on the side here. All divided by 3.84 times 10 to the 8 meters. Square root everything. Put that into your calculator and remember to square root. And our final answer is 1.02 times 10 to the 3 meters per second. And you can say around the Earth as a direction of travel for the moon. So once again, because we're looking for a velocity, we need to replace our centripetal acceleration formula with one that deals with velocity. Let's now try an equation or a problem with a period. So here we're asked to find what is the mass of a planet if its moon has an orbital period of 25 days and an orbital radius of 2.50 times 10 to the 6 meter. First thing we notice that we're given days, but in our equations we need to deal with seconds. So converting days into seconds, we find that it is 2.16 times 10 to the 6 seconds. So again, with our free body diagram, here's our planet, here's our moon, and the only thing on the moon that affects it is the force of gravity. So Fnet equals the force of gravity. So Fnet is the mass of the moon times the centripetal acceleration equals big G, mass of the moon, mass of the planet, all divided by r squared. First thing we notice is the mass of the moon get cancelled out. And now we are asked to find the mass of the planet. Also, we also need to substitute out our centripetal acceleration. Now, because in this equation we are given a period, we need to substitute the centripetal acceleration with a formula that deals with period. So the left side becomes 4 pi square r over t squared, and then the right side remains g, mass of the planet, divided by r squared. We're looking for the mass of the planet, so let's isolate for the mass of the planet. So mass of the planet equals 4 pi squared r cubed, because now we have to move the r squared onto the other side. So then r times r squared becomes r cubed, all divided by g and the square root of the period. So now let's do some substitution. Equals 4 pi squared r we are told is 2.50 times 10 to the 6 meters. That number is cubed, all divided by 6.67 times 10 to the minus 11 newtons meters squared per kilograms squared. And our period, we are told it is, or we converted it is to 2.16 times 10 to the 6 seconds. Don't forget to square the period. And then we put everything into calculator. Please be careful when you're calculating, because you're dividing by two numbers in scientific notation and you're squaring one of them. So please be really, really careful into how you put it into your calculator. And our final answer is 1.98 times 10 to the 18, and the only unit that gets left is kilograms. So what are satellites, especially Earth satellites, good for? Well, they're usually good for things like communication, so television, internet signals, weather predictions, or detecting forest fires, and just sort of information gathering such as spy satellites. Now, around the Earth, there are two kinds of satellites. The first kind is what we call geostationary. They appear to be stationary to an observer on Earth. This is really good for satellites for communication because you don't need to re-aim your satellite dish. So things like satellite TV uses satellites that are in geostationary orbits. They appear to be parked, and they don't move over the sky. The second type of satellite are lower altitude satellites. They change their position relative to the ground. So all of our GPS satellites, if you have an app that shows a GPS satellite, you can see that these satellites slowly move across the sky. Satellite phones also have satellites that move across the sky, move over different places over the sky, as well as spy satellites and weather satellites. Now in Canada, we have what is called RadarSat, which we use to monitor growth of forests, farmland production, and things like that. Now, unfortunately, there is only very limited room for these satellites because all satellites have to have a certain orbit, and the further away you are from the planet, the slower it travels, according to Kepler's law, and the lower the altitude of a satellite, the faster they travel. There is a email that you can sign up with NASA to determine the position of different satellites, and at just the right time of the day, right angle of the sun, and so forth, you can actually see many different satellites across the sky. Now, these satellites move very quickly over the sky because they are not in a geostationary orbit. They change their position relative to the ground. In fact, geostationary satellite, the period for geostationary satellite, of course, is then 24 hours. Because if the Earth requires 1 day or 24 hours to make one orbit, for the satellite to appear stationary, it also needs to have the same period. For lower altitude ones, for satellites that move, so for example the International Space Station, their period is as short as 90 minutes. Another good point to note is that when we talk about satellites, most people on Earth talk about orbital heights. And that is the height above the surface of the Earth. However, when we do centripetal acceleration questions, or satellite speed and velocity questions, we need to consider their orbital radius. That is all of the distance from the satellite to the center of the Earth. And those two distances could be very different depending on the satellite involved. So now let's try one last question, this time dealing with an Earth geostationary satellite. Here we're asked to find what is the orbital height, so h equals question mark, of an Earth geostationary satellite. So because we know it's geostationary, we know that the period is 24 hours. And when we convert that into seconds, it is 86,400 seconds. And we know the mass of the Earth is given to us as 5.97 times 10 to 24 kilograms. And our radius of the Earth is 6.37 times 10 to the 6 meters. So we are given this, the radius of the Earth, so that's the radius of the Earth, and we're asked to find the orbital height. So that means at first we need to find the orbital radius and then subtract out the radius of the Earth. So once again, we have our free body diagram, and from that we know that the Fnet equals Fg. Fnet is the mass of our satellite times centripetal acceleration, and force of gravity is big G, mass of the satellite, mass of the Earth, all divided by r squared. R squared in this case, remember, refers to the orbital radius. So again, we notice the mass of the satellite gets cancelled out. And now we need to substitute AC with one of our centripetal acceleration questions, or equations. And we know that we're dealing with a period, so we're going to replace it with 4 pi square r over t squared. And on this side, we have g, mass of the Earth, divided by r squared. And we're looking for the radius, which appears in both sides of the equation. But we can collect the like term and manipulate our equation appropriately and correctly, so that r is t squared times g times the mass of the Earth, all divided by 4 pi squared, and that is all to the cube root. So then we plug in some numbers. T is 86400 seconds, don't forget to square, times G, 6.67 times 10 to the minus 11, newtons meters squared per kilogram squared. And the mass of the Earth is 5.97 times 10 to the 24 kilograms, all divided by 4 pi squared, all to the cube root. If we punch it up correctly into our calculator, once again, be careful that you're dividing by two numbers here, and a whole lot of scientific notations, so make sure you enter your numbers into your calculator correctly. We find that the orbital radius is 4.22 times 10 to the 7 meters. So we found the orbital radius. However, we need to subtract out the radius of the Earth to find the orbital height. So the orbital height is 4.22 times 10 to the 7 meters, which was our orbital radius, minus the radius of the Earth, 6.37 times 10 to the 6 meters. And our final answer is 3.59 times 10 to the 7 meters. So another way of saying this is that orbital or geostationary satellites have an orbital height, a distance above the surface of the Earth, of some 36,000 kilometers. That is a really far distance, and yet we can get really good, accurate satellite data from geostationary satellites. So that means their strength, their equipment must be very strong and capable of transmitting our signals a distance of 36,000 kilometers from the surface of the Earth. So hopefully you found these examples very informative and can help you solve all sorts of satellite-related questions.